We can see it. We can see the other chat as well, by the way, the Zoom chat and some other things. So nice.
Okay. So,
okay. Over to you.
So hello everyone. I'm Enric Tejedor from the Root team, and today, together with Stefan Wunsch, we're going to tell you about this new PyROOT that we released as default with Root 622 just a couple of weeks ago. The structure of the presentation will be, first I will present some slides. So I will introduce what PyROOT is, and I will just give you some highlights of some features that are available. And then in the second part of the presentation, Stefan will give you a demo, so in the form of notebooks. So some of these features that I'm going to mention now, you will see them in more detail in the notebooks later. Yeah, so just to give an introduction about what PyROOT is. So PyROOT implements Python C++ bindings. So you can use PyROOT to use root from Python, right? But not only, and I think this is an important point to make, PyROOT also gives you access to any C++ code. You can call into any C++ thanks to PyROOT from Python. And this is possible because PyROOT is a special type of bindings. It's what we call automatic or dynamic bindings, in the sense that you don't generate any static wrapper for your C++ classes, or you don't provide any special type of file or modify your C++ code. Everything happens kind of out of the box, because PyROOT is able at runtime to find information about C++ entities that you want to use, and then it gives you back Python proxies to those functions or classes, C++ classes that you want to use in your application. And this is all powered actually by root, by the root type system, and the C++ interpreter, Cling, which are the ones that provide this runtime information, this reflection information that allows you to create objects and run functions, methods on them at execution time. And then on top of that, we have what we call Pythonizations. So for us, a Pythonization is just a piece of code that makes it easier for you to use a C++ class from Python. Say easier or more Pythonic, right? So I'm going to show an example of it now. I'm going to show what we mean by automatic bindings and what we mean by Pythonizations exactly. This is a very simple PyROOT script. The very first thing that you usually do, you do import root, right? The root module. And then let's assume that we want to create an object of class tfile. So tfile is the C++ class in root that represents a root file. So we are invoking the constructor of tfile from Python. And here it's important to point out that there is no Python tfile class. What actually happens here is that in this lookup, when we do the root dot tfile and we pass the arguments, we are going to interrogate the interpreter. We are going to say, look, the user wants to create an object of class tfile with these arguments. And then dynamically, we are able to create that C++ tfile. And what we return to the user is actually a proxy, a Python proxy to that C++ tfile. So the Python proxy has in its belly the C++ tfile and just redirects the calls to that C++ object. That's what we mean by automatic bindings. And then Pythonizations are some extra behavior on top of the automatic bindings. Like you see in the third line here, now that we have the file, we want to access some content of the file. In this case, we want to access the T3 that is inside the file. The fact that we can do this with this syntax f.myTree, where myTree is the name of the tree, is thanks to a Pythonization. So it's some code that makes it possible, or that intercepts this dot, goes to the C++ T file, gets out the C++ T3, and returns a Python proxy for that T3. Right? So that's the idea of a Pythonization. This example is about root, but I mentioned that PyROOT is not only about running root code. So here what you see is an example where we are in Python and we declare a variable, a string variable that contains some C++ code. In this case, it's the definition of a function, f, and the definition of a class. What we can do with PyROOT is we take the C++ code and we give it to the interpreter. And we say to the interpreter, process this code. And immediately after that, from Python, we can actually call into that C++ code. We can create an object of class A, as you see here. Let me just maximize this. An object of class A, as you see here, and then also a call into the function f. So this demonstrates that it's not only about root that PyROOT can work on. It can also dynamically process and call into C++ code thanks to the root interpreter. So that was it for the introduction. Now I wanted to talk about the features of this new PyROOT. Like I mentioned, we have this new root release 6.22 that comes with the new PyROOT. This PyROOT, I actually already talked about it in previous PyHEPs, but previously it was in experimental mode, right? So now it's the default. So now if you install root 6.22, you are getting this PyROOT as default. And it's a major revision of the bindings, and it has many new features. I'm going to highlight some of them. One of them is this new structure. The new PyROOT is actually built on top of CPPYY. CPPYY is a set of Python libraries that implement the automatic bindings. So they take care of things like the creation of proxies, or they convert types from Python to C++, right, using the Python C API. That's what CPPYY does. And on top of that, we add our PyROOT layer, which is basically the Pythonizations that we implement for our root classes. And of course, everything rests on top of root and the C++ interpreter clean, which are the ones that power the automatic bindings. What's the immediate advantage of this new design, of this new structure? So one advantage is that thanks to CPPYY, we have improved C++ support. We support more C++ than before in the old PyROOT, and more modern C++. Things that did not work before, like move semantics or variadic templates, like you see in this example here. This is just an example of a function with variadic templates, and then you see how we make the interpreter process it, and immediately we instantiate it and call it from Python. This was not possible before, and it's possible now, thanks to CPPYY and the new bindings. Another nice feature of the new PyROOT is this interoperability with scientific Python libraries. So yesterday in the survey, pandas and NumPy were mentioned as one of the most used in our community, or at least among the attendees of this workshop, right? So we have worked on making some of our classes interoperable with these libraries in Python. I'm not going to talk about all of them. I'm just going to mention a couple. One of them, which is important, is our data frame. So our data frame is our data frame-like class in root. So you can use it to load and process root data. So for instance, a T3 that is stored in a file or a set of files, right? So with this R data frame, you can load the data set and process it with operations like transformations, like filtering columns, defining new columns, and all happens in C++, because if you look here, these strings, they are C++ expressions, right? So even if you use the Python interface, under the hood, what is happening, it's that C++ is running. Another nice thing is that you can actually run these in multi-threaded mode. If you call this root enable implicit NT, the workflow of your R data frame computation will actually run on the cores of your machine. So we are able to spawn several tasks to process it in parallel. And once you have processed it, right, your initial data set, you have transformed it, you can run this as NumPy, which allows you to get the columns of your data set as NumPy arrays. What you get back actually, this np_arrays is a dictionary that contains these columns as NumPy arrays. And then you can actually, if you want, you can also go to pandas. You can pass the result of as NumPy to create a pandas data frame and then work with pandas. We're going to see a more elaborated example of this in the demo. Then another example of interoperability, again quickly, because we're going to see it in the demo, is when you have a C++ container, like an std vector, you have it in Python, but you want to work with its data as an NumPy array. You can do this np.asArray of the vector, and then what it does is it just adopts the memory of the vector. There's no copy, but from that point on, you can use it as a NumPy array. Then another feature that we have recently added is this number declare feature. So this allows you to decorate Python callables, Python functions, and run them from C++. So what we do when you decorate your Python callable like this with this number declare is that we are going to generate a C++ wrapper for it. And this C++ wrapper will invoke a cheated version of the Python callable, a cheated version with number. How is this useful? This can be useful, for instance, we had users that wanted to use this from our data frame. Imagine that you have an R data frame workflow and you want to use some Python callable from your R data frame workflow. You can decorate it like this, and then, for instance, in a define, you can actually use it like this, right? So this is actually the C++ wrapper that we generated, and this C++ wrapper will call into the Python call. Now, change of topic, Multipython builds. So of course, the new PyROOT has support for Python 3, but we also keep support for Python 2, because we know that still some code in the experiments is implemented in Python 2, so there has to be still a transition to Python 3. So in order to help in this transition, we added a new feature, which is you can have a single root build that is built for both Python 2 and 3 at the same time. So it generates the PyROOT libraries, both for Python 2 and Python 3. And the way it works is that if you build root in your system, by default, if it finds both Python 2 and Python 3, it will build PyROOT for both. But then you can also steer a little bit this behavior. You can tell it hints like, look, I don't want to use the system Python. I want to use this Python installation that I have here. That's also possible. Or you can also keep the old behavior. You can say, look, I just want to build for one Python version. Just this is the Python that I want to build for. That's it. Yeah, so if you want more information, I included a link here with all the details about this. So this was already put in production. It's being used by CMSW already. So right now, you can configure your environment with a given CMSW stack, and PyROOT will be in the stack, and it will be accessible both from Python 2 and Python 3, because there's a single root build that has been built for both Python versions. Documentation. Documentation is something that we received a lot of requests for because it was lacking in the past. So we are putting some effort in this. We recently published this new website of Root. This is how it looks like now. You can check it out. And this website has a manual section and in particular a PyROOT manual section, which has things like how to use the PyROOT user interface, or what are the configuration options that you can use, or how you can do interactive graphics. These kind of things, they are all in the PyROOT manual. There's already some content, so you can check it. And then on the other hand, what we will provide as documentation as well is we have this reference guide where we'll put the documentation of our C++ classes. So what we will do is that when you look for the information about a particular C++ class, you will find the C++ information and also the PyROOT or Python related information, like what are the Pythonizations available for that class? How can you use that class from Python? So this will also be provided. Yeah, so I want to move already to the demo, just some quick summary. So important message, we have a new root release 6.22 that has this new PyROOT, has the features that I just described and what we will see in the demo. I included a link to the installation instructions. As future work, there are some things that didn't make it into 6.22, but we still want to work on, so just for people to know, like the installation in standard Python directories of PyROOT. This is still in the list. Giving the user the possibility to define their own Pythonizations, not just for root classes, but for user classes. Or also extend the programming model of our data frame for Python. It's a few things that we want to do rather soon. So let's move to the demo.
Let me take over.
Yeah,
can you confirm that you hear me?
Yeah, I can hear you.
Perfect. Can you quickly stop sharing your screen? Oh, I can just kick you out.
And just so you're both aware, well, Stefan, you've got in principle 12 more minutes, and you've got a lot of questions coming in, so it'll be nice to.
Oh, well, I will speed up. Can you see my screen?
Yes, perfect.
Yes.
Perfect. So let me quickly highlight a few goodies we think which make PyROOT great. Sorry? Okay, fair enough.
Make it a larger font. Can you make it physically bigger?
So, like that.
Much better. Thank you.
Much better. Perfect. So I want to show you how efficient Python looks like with PyROOT and how you can leverage the dynamic C++ and just-in-time compilation to make this happen. So one of the core features of Root and also PyROOT is that we have a just-in-time compiler cling. And what you can do from PyROOT, as Enric has shown before, you can use the interpreter to compile to implement the functionality you need, which has heavy load. Like here, an n-squared problem, you will want to find the largest sum of two vectors, vector 1, vector 2, of a specific size. So you make a double nested loop, you find the largest sum of pairs, and you return it. Now let's see how this looks from Python. Now we can interact. So let's load in some data. What we offer is you can make, for example, NumPy arrays. So NumPy is the data interface in Python. We all know that. Now how convenient it is to throw the just-in-time compiled function on this data in NumPy in Python. It looks like that, like root.largest sum. The name is the same as the just-in compiled function, and you can just run it. And what you get, and what I want to show, is that it runs in 50 microseconds per round. So this doesn't tell much, because let's compare it to something else. We can re-implement that thing in Python. It looks nice. It's the function here, and run it again. And as we see it already now, it takes quite some time. And it runs in around 5 milliseconds. So that means it's actually around a factor of 100 slower. And that's what means efficient Python. We want to be in Python because it's convenient, but as well, if you have a lot of data, we want to run fast. And that's what PyROOT offers. But that's not the end of the story. Because probably you say, okay, I have even more data and I want to be even faster. And that's what you can do then in PyROOT, and what we offer is you can push the implementation not to a just-in-time compiled thing, but you push it in a header and a source file. You call g++ ofast shared, so you make a shared library, highly optimized, and you can just load it into your Python runtime. Like this, you the interpreter, you load the library, and there we go. And finally, we can call it the same thing as we've seen before. We call it in v1, v2, which are NumPy arrays. We call it through the root.optimize_sum, and we'd see it runs in around 10 microseconds. So let's go back a little bit up. We see 10 microseconds compared to 50 microseconds is a factor of 5. Compared to 5 milliseconds, it's a factor of 500. So that's what I meant with efficient Python, and how you really can come from Python, steer in Python, and still have super efficient code like NumPy, for example, in the backend, but highly optimized and highly customizable to your specific problem. You can do whatever you want. The second part of Python-based analysis features we have in PyROOT is the interoperability. we've already seen a little bit of this before, but let me highlight again that one thing. Let's say you come from C++ and you get some data. That happens if you come from C++ framework and we're just doing complicated stuff, let's say. And then you get back a container from C++. Container C++ means often a standard vector. Now what PyROOT does for you is we attach the array interface of NumPy to such suitable containers. And then you can call NumPy as array and you get back a NumPy array. For example, here you see root standard vector, the content is 1 to 3, NumPy array 1 to 3. Now, but the nice thing I want to show is you can change the first element of the standard vector, so of the C++ object, and it changes also, as you see here in the NumPy array, which means we adopt memory. We don't copy as long as we don't have to, and that makes it very efficient to deal with large amounts of data, which is basically the target of root. We support the same thing the other way around. So you take a NumPy array, then we have the function root vec_ops as our vec. Our vec is basically a standard vector which can adopt memory, and you see here the same mechanic. Let me jump over this, and let's go to data frame, the last thing I want to show. So another use case is you have data in root files, you want to have it in Python as NumPy arrays. We attached it, as Enric has shown before, to data frame and just more detail. You make a data frame, you can read data from here via XRD, some open data. And then the workflow, the idea is to have a highly optimized computation graph, a tool chain in C++, which can run multi-threaded. We can make filters, defines, we transform the data set. And once we're happy with what we have, we call as NumPy. We specify the columns we want to have, and we get back a dictionary of NumPy arrays. And now you can do stuff like, okay, take pandas, make a pandas data frame. Oh, there's the data. Or I want to plot it with matplotlib, and we see there's the set peak. You can do the same thing the other way around. You have the data in a dictionary of NumPy arrays. You can make a data frame, a root data frame out of it, use parallelized C++ performance, and for example, do everything you like. For example, snapshot, which means you write it to a file, and then here you see the file structure. So that's it. So that's I won't talk in detail about this notebook. I just want to show you that this is how actual efficient analysis in Python with root and PyROOT looks like. And then you get like physics examples like a dimuon spectrum, or other Higgs analysis for leptons, gamma, gamma. And there are all the links where you can try and do it by yourself. Everything with open data, open code, open source. So that's it from my side. I think we're happy to take questions.
Thank you very much, both Stefan and Enric. Really good overviews. I'm really sorry that I pushed you a little bit at the end, but you've got a lot of questions come through, 23, which I think might be the record so far. So obviously, it's a very exciting community. I can see Geddes has raised your hand, but I'm going to stick with what we've suggested by taking the top questions of Slido. And if we have time, I'll come back, but I think I'll have to encourage you to go to Slack otherwise. So in the interest of time, shall I share my screen for the questions, or would you like to do it?
Go for it, please.
Okay, so you can see, here we go, questions. So first question, I'll read from the top. Lucas has asked, what's your opinion on uproot?
Yeah, so maybe Stefan, I can start with this one. So when uproot appeared, it had a very good thing, which was that it made it possible with just a pip install for you to read root files into NumPy format. And this is something that we have tried to compensate for, like, for instance, providing the conda package for root, so that with conda install you can also have root, right? And that makes it easier. Then maybe I can mention about the programming model that I see and how it compares, for instance, or using PyROOT and our data frame and then going to NumPy. So it seems to me that uproot relies more on a Python-based programming model, right, for the not only the reading of the files, but also the manipulation of the arrays afterwards. And we kind of in root, at least as for now, in our data frame, we push this more to C++, right? It's not done in Python. The number declare functionality that I described goes a little bit in the direction to allow people to do more things in Python. So that's definitely something that we want to work on as well.
Let me hook in. A last thing I want to mention is uproot is not root IO. That's another thing. So root IO, what we can do with PyROOT and what we offer is that you can read everything, all your C++ stuff. So like basically everything you can serialize with root. That's another thing where is a difference, which you probably have to consider, which doesn't kick in for many analyses because everything is float and double and fundamental types. But still, that's one of the core functionality for root, which has to be kept in mind.
Thank you both. I mean, I just want to add that I think what I've seen has been certainly what you showed, and then compared to a couple of years ago, it's really impressive development. And I think it looks to me from the outside like a really nice relationship building between uproot and the root team. So I think that's really it's really fantastic to see all the developments that you're putting in and everything you showed. Should we take the next question then? Do you want to talk a bit more? Well, okay, I guess it's actually, I will skip because I don't want to be too focused on this. Let's go down to the next one then, slide 14, and number. Why has root put its own decorator instead of using the number decorator defunct?
I can comment on this. So the idea is to provide a backwards way. You implement something in Python and you want to use it in C++. That's, for example, the case for our data frame. And there you need a defined signature. Of course, you have this also with cfunc, but you want to translate it to the C++ types directly, and we want to make it simpler, basically, than using cfunc. That's the main idea. So it's usability at the end, I would say. Even in the back, we use cfunc. We use number to JIT. So it's just a convenience wrapper around it.
Ben, you are muted.
You're muted, Ben.
Oh, that's a classic, isn't it? I was suggesting, we reached about time, so I'm afraid we'll move on to the next one. But what I will do is make sure all these questions get distributed. It's great to see the interaction. Thank you very much to both of you. And I'll allow these questions to stay up for about 5 more minutes, and then I'll export them and provide them on Slack. And I can see a few of these questions have had answers in line from some people already. So thank you once again, both Enric and Stefan.
Thank you.
Really good to see the progress.